Hello, my name is Angelos Mavrogiannis and I am a second-year master's student in the Mechanical Engineering Department of Carnegie Mellon University. I am also a member of the Intelligent Control Lab at the Robotics Institute, where I am being advised by Professor Changlu Liu. My project is focused on human driver behavior classification from partial trajectory observation. Autonomous vehicles are gradually becoming a part of our lives. A lot of money and resources are being spent on autonomous driving research, both in the academia and in the industry. However, there are several key challenges that are not allowing autonomous vehicles to be massively deployed in public roads. A key challenge lies in the fact that autonomous vehicles have to deal with mixed traffic scenarios. An important point to raise here is the big difference between a human driver who is flexible and adaptable and the autonomous vehicle, which cannot be as reliable as a human. In this example, the autonomous vehicle on the left is trying to merge in the right lane. But is the human-driven vehicle going to allow it to successfully merge, or is it going to block it by accelerating? We need to be able to ensure safety in these traffic scenarios. We need to be able to avoid dangerous situations, mitigate the possibility of accidents, and maintain a steady and efficient traffic flow. To do so, we need to be able to estimate the human driver's future actions and trajectories. There's been a lot of existing research in trajectory prediction, for which I did an extensive literature review. And what I noticed is that human driver personality aspect is currently being ignored. A few relevant works which are trying to classify human driver behaviors have certain limitations. The first one is based on a user study, which can be biased, and the second one is computationally expensive. On the other hand, our approach is computationally efficient since it is based on the PCA and K-means clustering algorithm, and it is also applicable for improving current techniques in prediction, planning, and control for autonomous driving. Our hypothesis is that leveraging inherent cues representative of drivers' personalities can lead to more accurate predictions for their future trajectories. This is an outline for our approach. First, we define a probabilistic model. Then we process the data, we perform dimensionality reduction, we form behavioral classes based on a clustering algorithm, and we perform online inference. Introducing some notation, we will use QTI as a state of an agent I at time t, and Q capital as a state of all agents. C is the historical trajectory information of an agent, and C capital is a multi-agent historical information. B calligraphic is a discrete behavioral space we need to define, and B capital is a tuple consisting of all behavioral classes of our agents. The trajectory prediction problem lies in the estimation of the probability of observing future trajectory sequence given a past trajectory sequence. According to our hypothesis, an agent's behavior heavily influences its future trajectory. Then we can use this to estimate P. To do so, we are using the Interstate 80 freeway dataset based on the MGSIM program, which consists of 45 minutes of vehicle trajectories captured in a 1,650-feet section of I-80 in California. We also defined a visualizer in Python, which you can find on this GitHub link. Next, we perform feature extraction. We believe that there are some descriptive statistics that capture the entire sequential behavior of a vehicle. And the measures we used are the average, maximum, and variance of lateral velocity and longitudinal velocity, the average lateral acceleration and longitudinal acceleration, the average relative velocity of a vehicle to its traffic flow, and the average relative velocity to its preceding vehicle. Next, we perform principal component analysis. We retain the first two principal components, which capture 54% of the total variance of our data. Next, we need to define the optimal number of clusters. We use the elbow method and the silhouette method. Both of them agree that we should use k equals 4. Based on k equals 4, we apply the k-means algorithm on our principal components, and we get the following clusters. Comparing our clusters, we can see that the maximum longitudinal velocity is increasing monotonically from cluster 1 towards cluster 4. On the other hand, the maximum lateral velocity is decreasing from cluster 1 to cluster 4, and the relative velocity from cluster 1 to cluster 4 is increasing. Based on this, we can say that 4 behavioral clusters have been formed. The most dominant feature is the longitudinal velocity. Since the lateral velocity decreases from cluster 1 to cluster 4, we can say that drivers whose speed tend to stay in their current lane. We can assign labels like timid, conservative, neutral, and aggressive to the formed clusters, and we can now use these clusters to improve trajectory prediction. Now we can see a timid behavior on the left and an aggressive behavior on the right based on our visualizer. Now that we have defined the behavioral classes, we can extend our mathematical model and focus on the estimation of this conditional probability. Then we can use a multi-class classification in an online setting to estimate it. We compare k-nearest neighbors, logistic regression, and a multi-layer perceptron. As we can see, the runtime of KNN and logistic regression is much smaller than this of the multi-layer perceptron. However, the multi-layer perceptron is much more accurate. Finally, what we are going to work on now is the first part of our conditional probability. If we assume that knowing the behavioral classes of our agents B, we do not need to know the past trajectory sequence of all agents C capital, then we can write this probability as following. Using a chain rule, we can write this probability as a product. And finally, using a Markov assumption, we can clip out the previous world states Qt. Next, we are introducing an extra product term in order to account for all agents. Finally, we are estimating this conditional probability through hidden Markov models. Thank you very much for your time.